So this section is on an overview of the solar system. We're just going to talk about what the solar system is, what's in it, how we identify different objects in it, what its overall size scale is, a little bit about the types of planets and smaller objects, and a little bit about how it formed. So let's get started. So the solar system is basically the sun and all the objects that orbit it, including planets, asteroids, meteors, dust, and gas. This is a complicated question because it's kind of like asking where the atmosphere ends. The atmosphere just gets thinner and thinner as it goes up, and so it's hard to define an ending spot. And so sometimes they'll say, well, just out to the end of Neptune. We'll talk about that as the solar system. But in fact, you can go way past that. The solar system, we can say, extends to about 1,000 astronomical units. Remember, an astronomical unit is the average distance from the Earth to the Sun. That's about 100 million miles, and so 1,000 of those would be 100 billion miles. For comparison, the farthest thing we used to call a planet, Pluto, is about 4 billion miles away. So it's 25 times farther. There's still gas and dust out there that is in the gravitational control of the Sun, basically, even though it's very only weakly controlled. And by the way, you can go way past there as well. You can go way past the 1,000 astronomical units. So it kind of depends on how you're talking about it, but it goes way out. The Sun comprises about 99.8% of the total mass of the solar system, at least within the orbit of Pluto. When you start talking about comets, we'll talk about that in a little bit, it gets a little more complicated than that. But so if you just take all the planets and the asteroids and the gas and dust, all the stuff that's within, say, Pluto's orbit or a little bit beyond that, the Sun is about 99.8% of the total mass. In other words, there's the Sun and a bunch of little stuff. Jupiter accounts for half of what's left. So Jupiter is about 0.1% of the remaining 0.2%, and that leaves 0.1% for everything else in the solar system. Saturn, Uranus, Neptune, Earth, Mars, Venus, Mercury, all the asteroids and whatever comets and other debris are inside that range. Let's talk about some objects in the solar system. There are two types of what we call large objects. Obviously, nothing is large compared to the Sun, but if you look at the objects that aren't the Sun, there are planets. Those are large objects, and there are 8 of them: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And it turns out, if you just look at them sort of objectively, there are 2 classes. We divide them into 2 groups. The large gassy ones are called Jovians, or gas giants. It's a little more complicated than that, but that's what we're going to say. The Jovians is what I usually call them. And then the small rocky ones are called terrestrial planets. So Mercury, Venus, Earth, and Mars are terrestrial planets. Jupiter, Saturn, Uranus, and Neptune are Jovians, or gas giants. By the way, you should know those in the order they exist from the Sun and so on. Oops. See if I can do this right. There we go. So we talked about the 2 types of large objects. Now there are 2 types of small objects. We call them asteroids and comets. Asteroids are small rocky objects from the inner solar system, mostly between the orbits of Mars and Jupiter. The largest asteroid is maybe 300 miles in diameter. There aren't that many of them. Well, we'll get to that in a second. The total mass of the asteroids in the solar system is smaller than the mass of the Moon. So if you scooped up all the asteroids in the asteroid belt, you wouldn't have the mass of the Moon. And now they're spread out over an enormous area, right? Their distance from the Sun is maybe 300 million miles or something like that. And if you multiply that by pi, so there's 600, anyway, maybe a billion miles of path to spread out 1 million asteroids or so, or a few million. So when you watch a science fiction movie and we're sending a spaceship through the asteroid belt and you see them dodging and weaving, it's nothing like our asteroid belt, if that's how an asteroid belt looks somewhere else or in science fiction. We send spacecraft through the asteroid belt and never worry about running into anything. The objects are very far apart in there. I think if you look at objects like a mile or bigger in diameter, they average something like 500,000 miles between them. So it's a long way. Anyway, they're far apart. And that's the asteroid belt. Now, here's where things get a little tricky. It turns out the total mass of comets is enormous. Comets extend way past the sun. So look at this bottom one here. Comets are icy objects in space beyond Neptune. Sometimes they're called trans-Neptunian objects. Most comets exist beyond Neptune, and they go way, 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 way out. Unlike the asteroid belt, which is, first of all, it's a flat belt confined to the plane of the solar system, and we'll talk about that in a minute. But also, they have, first of all, they're 3D, so they're going in all angles and stuff around the sun in circles that are in all kinds of planes, and they extend way, way out. And so if you actually try to account for that mass, they add up to about 2% of the mass of the sun. So that's an enormous amount of mass. That's 20 times the mass of Jupiter or something like that, as opposed to comets, which just add up to the mass of the moon. So asteroids account for a lot of mass. There's a lot more asteroids, maybe 100 trillion of them. Obviously, it depends on how you count them, right? What constitutes a comet? How big does something have to be before you count it? So the largest comets can be maybe 100 miles in diameter. Pluto and the other extrasolar planets, which we'll talk about in a second, like Eris, not extrasolar planets, dwarf planets, like Eris and Makemake, have the constituency of a comet. They're basically icy, rocky objects like comets. And so they're just large ones. We don't call them comets, we call them dwarf planets, but they're just large comets, basically. It's one of the reasons Pluto got kicked out of the club. Okay. So just to give us a sense of scale, let's make a scale model of the solar system. And so we're just going to shrink it down so that it's a more manageable size. So we're not talking about billions of miles, because that doesn't mean much to anyone. And so let's talk about the solar system, where we're making a model where the distance from the Earth to the sun is 1 meter, and everything else is scaled accordingly. It's like you have a cookie recipe for 20 cookies, and you want to make 200 cookies, so you have to multiply everything by 10, right? Here we're going to divide everything by about 10 billion or something like that. And we're going to end up with an Earth-Sun distance, 10 million. We're going to end up, closer to 2 billion. Anyway, we're going to end up with an Earth-Sun distance that's about a meter. That's about 40 inches. So you should have some idea of what that distance is like. So Mercury is about 40% the distance from the sun that the Earth is, and so that makes it 0.4 meters, or maybe 16 inches or something like that from the sun on that scale. Venus is 0.7 times that, so that's maybe 28 inches. Mars is about 1.5 meters, or 60 inches, or 5 feet from the sun. So on a scale where Earth is 40 inches from the sun, all these guys are within about 5 feet of the sun: Mercury, Venus, Earth, and Mars. And that's it for the terrestrial planets. So we have a model of a sun in our solar system, in our little scale solar system, that it would all fit easily in a room. Now we can say, all right, let's look at the Jovians. Well, it turns out on this scale, Jupiter is about 5 meters from the sun, or 16.5 feet from the sun, 3 times as far away as Mars is. Right? Saturn is twice as far away as Jupiter, or 33 feet. Uranus is twice as far away as Saturn, or 66 feet, and Neptune is 3 times as far away as Saturn, or 6 times as far away as Jupiter, or 30 times as far away as Earth, about 99 feet. Right? So about 100 feet. That's a long way, right? 30 meters is maybe 33 yards or something like that. Hopefully you can sort of imagine what that is on a football field. So these Jovians are spread way out in comparison to the terrestrials, which are as far away as 5 feet, right? Pluto, I know it's not a Jovian or a planet at all, but just for fun, it would be 40 meters or 130 feet away about. So again, the terrestrials are all within 5 feet of the sun. They're packed closely in around the sun in our model. And the Jovians are spread from 16.5 feet to 100 feet. So let me say some other things about this scale. On this scale, if we were to include the actual sun on this scale, it's about 1/100th of the distance between the Earth and the sun. That is to say, 100 sun diameters would get you from the sun to the Earth. So on a scale where the Earth's sun distance is a meter, the diameter of the sun would be about a centimeter, 100th of a meter, or a little less than half an inch. So that's how big the sun would be, as big as your pinky is thick or something like that. Not wide, but the thickness of your pinky, right? Also on that scale, the Earth would be 1/10 of a millimeter, or a 250th of an inch. In fact, it's really not possible to develop an accurate scale model of the solar system that gets both the distances right and the sizes right. It would be ridiculous to try to make a model that had the Earth that was 1/10 of a millimeter. That's the thickness of several hairs or something like that. It wouldn't be a useful model. Of course, Mercury and Mars would be even smaller. Also on this scale, the distance from the Earth to the Moon is about 2.5 millimeters, or about 1/10 of an inch. So on a scale where the distance from the Earth to the Sun is a meter, the distance from the Earth to the Moon is about 1/10 of an inch. It took the astronauts 4 days to cover that distance. So this should give you a sense of the size of things, right? It took close to 10 years for the New Horizons spacecraft to travel from the Earth to Pluto. And it was the fastest spacecraft that's ever traveled. So it takes a long time. Finally, on this same scale, where the distance from the Earth to the Sun is a meter, the nearest star to the Sun, whose name is Proxima Centauri, that's the nearest star, would be 150 miles away on a scale where the Earth is a meter from the Sun. So people talk about how long it would take to travel to the nearest star. Even just the nearest one, it would be an extremely long distance. And an extremely long time to travel it. So let's take a minute and look at some planetary data. And hopefully this is readable. It is to me anyway. So these are the planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And they include Pluto as a typical dwarf planet, right? And so these are the terrestrials, these are the Jovians. I call these all gas giants also. Sometimes the outer two are referred to as ice giants. They also have gas on them. They've just got more ice because they're out where it's colder, and we'll talk about that in a minute. So let's look at the masses here. Look at the mass of the 4 terrestrials. So the number that this is multiplying is 10 to the 24th kilograms. Clearly representing the mass in kilograms is a little silly, because you need a 1 with 24 zeros just to get to Mercury. But it doesn't really matter too much what this is, and I'm not going to test you on what these numbers are. I just want you to look at sort of the trends here. So Mercury is 0.3, Venus is 5, Earth is 6. I'm just giving round numbers, and Mars is 0.6. So all these are between 0.3 and 6, right? Notice Earth is about, I don't know if you can do the math on that, but Earth is about 20 times more massive than Mercury and 10 times more massive than Mars. And Venus, which we sometimes call our sister planet, is pretty close to the same mass as the Earth. It's all between 0.3 and 6. Now let's look at the mass of the Jovians. Jupiter is 2,000 on the same scale. Saturn is about 500 or 600. Uranus is 90. And Neptune is 100 on a scale where the Earth is 6. Jupiter is about 300 times the mass of the Earth. And so the terrestrial planets are small, and we've already established that they're near the Sun. So they're small in mass, and they're near the Sun. Now let's look at their diameters, right? You're going to see a similar trend, right? These are in kilometers, and it doesn't really matter what the distance is. This is just under 5,000 kilometers. The Earth, Venus is 12. The Earth is almost 13. Mars is almost 7. And so these vary between about 5 and 12 or 5 and 13, something like that. And how the outer planets, Jupiter is 142, then 120, then 51, and then 49, so 50 and 50. So the outer planets, the inner planets are smaller, they're less massive, and they're closer to the sun. Right? And we really have two classes of planets here, right? This is why they're divided up into two types. Now let's look at their density. Your density says something about your chemical composition. And I'm going to have to remind you just a little bit about what we said earlier about density. We talked about the density of water as being 1, but the unit on that was grams per cubic centimeter. This is kilograms per meter, and so it increases this number by a factor of 1,000. It doesn't really matter what it is. You can see that Mercury, Venus, and Earth certainly all are very close to the same overall average density. Mars is a little lower, but still about 4,000, right? If you remember, rock on this scale, granite or something, would be about 3,000. So their average densities are greater than the typical rock that we find because they've got some metal in them. And the inner ones, before you get to Mars, have a little more than Mars does. We'll explain why as we go. Now let's look at the outer 4. 1,300, 700, 1,300, 1,600. Clearly, a different chemical composition, right? These are all rocks and metals. These are all close to the density of water. Remember, on this scale, the water would be 1,000. So these are like ices, and that's why they sometimes call them ice giants. Right? They have lots of frozen hydrocarbons in them. We can look at the gravity. It's a little less interesting. It's interesting in a different way, I guess. Notice that Venus and Earth have about the same gravity, but it's not too different than these three guys, Saturn, Uranus, and Neptune. Even though they have a much bigger mass, they've also got a much bigger size. And if you remember the formula for gravity, the size is in the denominator, and so it kind of cancels out. These planets have much more mass, but they're fluffy. And Jupiter's isn't that much bigger. It's just a factor of 2. When you take into account the fact that it's got 300 times more mass, it's only got about double the gravity. It's kind of interesting, right? Here's some other interesting factors. The length of the day. These are just kind of all over the place, but Mercury and Venus have very slow days. So these are in hours. So an Earth day, which is down here, is 24 hours. And then Mars is pretty close to that, but Venus and Mercury turn very, very slowly. Look at the Jovians. They're all faster, spinning faster than the Earth. The fastest one is Jupiter. It's spinning, it does one rotation in about 9.9 hours. Even though it's got all that mass and that enormous size, it's actually spinning really fast. Right? Here's the distance from the sun. We've talked about that already. And now let's talk about the temperature. These are in degrees Celsius. And I'll try to give you a picture that water boils at 100 Celsius, right? And so the average temperature on Mercury, which we may talk about that more in the future, doesn't make too much sense because Mercury is either in the sunlight where it's really hot or in the dark where it's pretty cold. So its average doesn't mean too much. But it's 167, so it's way over the boiling temperature of water. But look at Venus. Venus is at 464 Celsius. That's about 860 degrees Fahrenheit, which is way hotter than the temperature of burning wood. Burning wood burns at about 450 degrees Fahrenheit. And so this is a very high temperature. Venus is actually hotter than Mercury, even though it's farther from the sun. The reason for that is because Venus has a very thick atmosphere. It's got about 100 times the atmospheric pressure Earth has. And Mercury has no atmosphere, so the heat easily escapes from Mercury, but it doesn't escape from Venus. Earth is about 15. Notice we get colder and colder as we get farther from the sun. Right? That has some significance for the composition of these planets. And finally, you can look at the number of moons. Right? 0, 0, 1, 2, 67, 62, 27, and 14. So The outer planets are much larger and have more moons. There are a variety of reasons for that. And by the way, these outer two planets may have more than that because we've had probes orbiting Jupiter and Saturn, which have found a bunch of moons when they were there. So it's very likely that if we visit Uranus and Neptune with a space probe, they'll find many more moons. Let me just do a last. So the Jovian planets have a greater mass, a greater diameter, a smaller density. The gravities are a little complicated. They spin faster. They're far from the sun. And they're at colder temperatures, and they have many more moons. Right. If we look quickly at Pluto, Pluto's representative of the dwarf planets, at least the dwarf planets that are in the outer solar system. Ceres is an asteroid. It won't fall really easily into this category. But notice, first of all, that Pluto has a mass that's about 1/30 of Mercury's mass. It's another reason not to have it as a planet. It's just super tiny by comparison to these other guys. Its diameter is about less than half of Mercury's. It's got a density that's not consistent with any of the other planets, really. It's somewhere between the terrestrials and the Jovians. It's got a crazy small gravity. It's got sort of a somewhere in the middle day. Its distance from the sun is extremely high, and it's obviously extremely cold because it's so far away. And it's got, even though it's super tiny, it's got 5 moons. So briefly, we'll say a little bit about the composition of the planets here. The Jovian planets have icy, rocky cores and hydrogen compounds, primarily as their compositions. They have things like, of the molecules, the compounds they have, water, ammonia, methane. You'll notice they also have a lot of just raw hydrogen in them, especially Jupiter. Hopefully we'll talk about that later as we get to Jupiter. You'll notice that these compounds they have lots of hydrogen in them. It turns out that the hydrogen, about 90% of the matter in the solar system is hydrogen. And so that means that molecules that have hydrogen in them are very common. And so if there's a carbon floating around, 4 hydrogens will bump into it. If there's a nitrogen floating around, 3 hydrogens. And oxygen, you grab 2 hydrogens, and so on. We talked a little bit about that before. I'll get to why there's so much of these in the Jovian planets. The terrestrial planets have rocks and metals, and so some of the rocks you find there are silicon dioxide or magnesium oxide or iron oxide or aluminum oxide. It turns out these are the compounds of rocks and metals. They're what's common in the inner solar system because it's so hot there. It turns out these things like water and ammonia and methane that comprise the Jovian planets or make up a large part of the Jovian planets can't make solids, can't form solids when it's hot, which is what's going on in the inner solar system. It's very hot in the inner solar system. These compounds can make solids, and so what we get in the inner solar system is planets made out of this kind of stuff. In the outer solar system, where it's cold, these things can freeze and make solids. You get a lot more of this stuff. What influences the temperature of the surface of a planet? Well, we've talked about this a little bit just before. It turns out how close it is to the sun, whether it's getting heat from its interior. All planets, well, I shouldn't say all of them, the ones who haven't completely cooled off to their core are getting a little bit of heat from their interior. The Earth is, for example. But the amount of heat we get from sunlight at the surface is much greater. It's less true in the outer planets, and Neptune, for example, is getting more heat from its core than it's getting from the sun at the surface of the planet. When I'm talking about the Jovians and I say at the surface, I just mean kind of where the gas ends, whatever the top of that gas planet is. It's not too easy to define, but it's at least a region. Right? So let's look at the orbits of these things. So in this picture, well, I kind of lost my place there. Oops, hang on a second. There we go. So the blue circles, or the blue shapes, whatever you want to call them, are the planets, and the red ones are the dwarf planets. And so hopefully you can see from this that the blue ones look extremely regular, and if you tilted this thing just right, they're in a flat plane. Less so the red ones. As objects get smaller and farther out, their orbits get a little more scattered and outside the plane. Even Pluto, if you look at Pluto, its orbit isn't very circular either, and it's certainly not in the plane of the solar system. Now, all planets, there aren't any planets that have exactly circular orbits, but of the 8 planets, all of their orbits are pretty circular. If I drew it on, if I showed you a drawing on a sheet of paper, it'd be hard to tell it wasn't a circle. Not true with the dwarf planets. They're kind of all over the place. So how do these planets move around the sun? All the planets and the dwarf planets orbit in the same direction. So if you're looking at that previous picture, and one planet is orbiting counterclockwise from the angle we're looking at, then they all are. And so that's an important piece of information. Everybody's going around in the same direction. Nobody's going backwards. Of the planets, not the dwarf planets, of the planets, they're all in nearly the same plane. And most of the larger dwarf planets aren't too far off that plane either. And so all the planets are in the same plane, orbiting in the same direction. With a few exceptions, all the planets rotate on their axes in the same direction they orbit the sun. So if we go back to this picture, if the Earth is going around here, somewhere in here, look how close the Jovians are, the terrestrials are, right, even in this picture. If everybody's going around, counterclockwise, going around this way, then they're also spinning that way as they're going around. So they've got kind of the same angular momentum direction, the same spin direction in their orbital axis as they do for the orbiting the sun. The 2 exceptions to that are Venus, that's rotating on its axis extremely slowly backwards. It's still orbiting the sun in the same direction, but it's almost at a dead stop in terms of its turning, but it's going very slightly backwards. And the other one is Uranus, which is spinning kind of on its side. So, but other than that, everybody else is following the rule. So essentially, all of the rotational motion is the same. This is a clue about how the solar system formed. So some clues about how the solar system formed. Let me see if I can, let me just switch over. Let me just draw a little picture here. So if you start out with just a giant ball of gas in space. So nowadays we have telescopes that can kind of see out into space and see giant objects. Let's see, I am backwards on this thing. So let me turn this around. All right, I'm going to pause for a second. So if you just have a random gas cloud in space, and these are all over in space, this could be enormous. This could be a light year across, way, way, way bigger than the solar system. On this scale, maybe our solar system would look like that, okay? But for whatever reason, and it happens all over in space, we get these large clouds of gas and dust, right? Well, they're so spread out that their gravity is really weak, but everybody gets a little gravity pulling it inward. The guys on the outside, if you're an atom on the far edge of it, all of the other gravities that are pulling on you from all the other objects are kind of pulling you this way. And so these clouds tend to shrink. It's also true, and I won't get into this either, but if you average the motion of all of these things, there's going to be some average rotation. And so you might have a rotational axis that looks like this, where the average is doing that. The average, this thing is turning this way somehow. It's kind of like saying, if I threw a million pennies out on the gym floor, more than half of them would be heads, or more than half of them would be tails. Your chances of actually getting the exact same number of heads and tails turns out to be extremely small. You would get something different. So on average, every cloud of gas has some average rotation. It might be small, but it's an enormous cloud. And so even if it's a small average rotation, it's going to be turning in some direction. And what that does is that causes the thing to shrink this way along the axis more than this way. Because when something's spinning, it tends to throw stuff outward a little bit. It's harder for it to compress this way if it's spinning like this. If you just stand in your room and spin around, your arms will tend to want to go out a little bit. And it's the same sort of idea. And so what happens with solar systems, they start out as large clouds of gas and dust. They have some orientation for their spin. It could be any direction. And then they shrink and flatten out along there. And so what you end up with later on, and we see plenty of these with our telescopes now. We see stars in all stages of formation. You might see something later on that looks like this. Where now it's still rotating this way, right? Over time, the centerpiece coalesces into a star, and all of these things kind of coalesce into eventually planets. First it'll just be peppered with these objects will bump into each other and make bigger and bigger particles because they'll just kind of glom onto each other. And then eventually they'll get big enough that they'll have a little bit of gravity and can pull on each other a little bit. And so over time, you'll just end up with bigger and bigger ones. And eventually, at some point, you'll end up with a star in the center and a few planets. We're looking at it edge on, right? You know, like that are going around. I don't know, draw that one out there, out there, and so on. I don't know. Anyway, you get the idea, right? They're orbiting this thing somehow. Right, not a very good drawing. And so this is just sort of a broad picture. I'll show you some more pictures in a minute of formation. The composition of the planet tells us a little bit about the clouds. So let's go back to this picture where I got a star in here, right? As this stuff collapses inward, it heats up. Even before this thing becomes a star, material falling in gets hot. It's for the same reason that things speed up as they fall with gravity. They get, oops, there we go. They get hotter. And so even before this thing starts nuclear fusion, which happens, we'll talk about how that happens, it gets hot. And so that causes the inner planets, all the material inside, can't have things like water in it because water won't make a solid. It won't clump up with stuff. It just stays a gas. But somewhere out here, there's a frost line. If you get far enough from the sun, and now you have ices that are solids. So ices are things like, you can have water ice, which is what we normally call ice, but you can also have ammonia ice or methane ice or propane ice, various gases that are common. If you get far enough from the sun, they'll make a solid. Turns out they can't make a liquid. You need atmospheric pressure for that, but they can make a solid. And so there's a whole lot more of that stuff, like I said, because there's so much hydrogen in the atmosphere, that these guys are small and rocky. And metally? Is that a word? But out here, they have in these two places. And so this is a description of what happens with the sun. So let me go back to the original picture here and say compounds that form at higher temperatures are rocks and metals. They have the highest melting and boiling points. So they can form planets in the inner solar system. Water, for example, cannot make a solid in the inner solar system. These things are all for clues and confirmation about how the solar system formed. How do the characteristics of other solar system help us understand our own? We see stars in a wide range of stages of formation. We can look at stars just in our neighborhood, but really all over. We've got pretty good telescopes. And they begin, just like I said, as large clouds of gas and dust that slowly flatten out and form a disk. And then the tiny particles in there make larger and larger objects. That process, by the way, is called accretion, where planets are formed from small particles that accrete into larger particles. So eventually these get to a size where they're called planetesimals. These are just pre-planets. Excuse me. And these eventually collide and form planets. And this is how solar systems form. And this is kind of what we see when we look at them. I'll just give you a few pictures. So these are Hubble Space Telescopes of stars forming in the Orion Nebula. These are, this is just all in one particular gassy area in the constellation Orion, which is an easily identified constellation, about 1,300 light years away, so not too far away. Remember, our galaxy is about 100,000 light years across, and so this is like 1% of the distance from across the galaxy to us. So, excuse me, yeah, okay. Anyway, those are pretty good rough numbers. Each image shows an embedded circumstellar disk orbiting a very young star. These different angles, seen from these different angles, some are energized to glow by the light from a nearby star, while others are dark and seen in silhouette against the bright glowing gas. So you can see all kinds of different stages of formation. Solar systems in the process of formation. Here's a, oops. This is in the constellation Taurus. You can kind of see it's in a later stage, but it's pretty cool. You can see that the gas is slowly settling out, and it's forming it's formed the disk, and you can kind of see where planets are going to be forming in there. We'll talk about that more as we go. And here's some questions. I'll probably add some to this, but these are just things for you to think about as you're studying.